Okay, today's lesson is limited to one big idea, and that's how to compute a conditional probability. And there's a whole page here of thoughts related to it. It takes into account some condition that's given, that's a for sure thing that has already happened. And it's easiest to pick out of the crowd when you see the word given that, or the words given that. So that's what we kind of hope for, is that we see the words given that in the problem stem itself. It's pretty simple if you have counts for variables. So if you can count cards, if you can count different color marbles, if you have a table that has counts, this is the easiest way to do it, because if you have counts, you really can just count your top and bottom numbers for your probability and be done. It's pretty simple. If you don't have counts, if you have relative frequencies, which are percentages, then you're going to need a formula. So the formula is actually so important that they put it in the formula list, so it's in your blue book. You will have that on the AP exam. So it's a biggie. If they put it in the blue book, it's pretty important. So if you have percentages, you're going to need a formula. So we need to learn that formula today. A word of caution is that wording can be tricky. If you see the words given that, it's absolutely a conditional probability. There's no question about it. But there's lots of ways to reword probability questions so that they are conditional, but it's not as obvious that they are. So there's something in the problem when they ask you to find a probability that assumes that there's some condition, there's something that's already happened, or some condition that's already been met, something that's already been done, some sure thing that has occurred, and it changes how you compute your probability. The notation is special. You've got to learn the notation. You need to learn to write it correctly, and again, the formula using correct notation is in your blue book. The probability of event B given event A. Event B, so B is what we're trying to find the probability of, given that A has already happened, is written probability of, you'll have to just take a look at it. This is read probability of B given A. It almost looks like a fraction bar, B over A, but it's not actually just a simple fraction. Although fractions are involved when we do the computation, and the order comes in handy, because what's given, what comes after that slash, is generally going to tell you what's on the denominator. A is the condition, or the event that's already happened, or the sure thing. Okay, so let's go ahead and just calculate some and see how it works, see how it looks. So on the next page we have a contingency table. We've not seen one of these for a few chapters, but contingency tables are pretty common in conditional probability questions. I need to lock my focus here. Hold on just a second. All right, maybe that'll be better. And some of the probabilities on this page are simple probabilities, and some are conditional probabilities. So we're going to kind of pick them apart as we go. In its monthly report, an animal shelter states that it currently has 24 dogs and 18 cats up for adoption. 8 of the dogs and 6 of the cats are male. Find each probability if one animal is selected at random. Okay, let's fill in the blanks. 8 dogs are male. Alright. 6 cats are male. So total males is 14. There are 24 dogs total. So that means we have to have 24 minus 8, or 16 females. There are 18 cats total. So 18 minus 6 is 12 cats that are female. The girls are running the place, it looks like. And then the total number of females then would be 28. And the total number of animals in either direction is 42. Remember that these totals are called the margins of the contingency table, and back in chapter 2 we learned how to write marginal distributions. We learned how to write conditional distributions. So this actually kind of links back to doing conditional distributions. Alright, so let's start. Think of this as a couple of columns of questions to try to squeeze them all in. Let's start in this left-hand column with finding the probability that a dog is female. That a dog is female, which means we're only looking at dogs. So a dog is actually a condition. It's given. It has to be a dog. So that means we have to put total number of dogs on the bottom. So your condition defines what's in the denominator. And for the dog to be female means it has to be a female dog. So I look in my table for female dogs and I find that there are 16 of those. And 16 out of 24 is 2/3. You can rewrite that as a decimal if you would like to. We don't need to. That's extra work. I'm not about extra work. Just simplify your fraction and move on. All right. The probability that a pet is a female dog. So we're going to pick a pet. Pets can be males or females. So for a pet, we need to be picking from the total. Any pet would do. So that means the bottom number is all the pets available, 42. And the probability that that pet is a female dog. So if I consider all pets, how many are female dogs? 16. So 16 over 42, which simplifies down to 8 over 21. Okay, those sound really similar. So the difference in the two is that a dog defines a smaller group to choose from, which makes this a conditional probability. So we're not using the total for our bottom number. We're using something from the margins that's not the total for the bottom number. Okay, a pet is a cat. So we're going to pick a pet. How many pets are available? 42. How many of those pets are cats? 18 total cats out of 42, which simplifies to 3 out of 7. So notice that I don't need any fancy schmancy rules for any of these. All I need to do is look at the counts. Okay, remember that your bottom number is always the group that you're choosing from. So this is your given group. Now in this next one, we want the probability that a pet is male given that it is a cat. Male given that it's a cat, which means I have to have a cat. Cat is the given. Cat is a for sure thing. So the bottom number has to be cats. Total cats are 18. Now the top number is a subset of the cats. So it's a male cat. Male cats, there are 6 of those. So if I have a cat, what's the probability that it's male? 6 of those are male. So 1 out of 3 cats are males. So this is for sure a conditional probability because we have those magic words given that, and the given is always going to be your denominator. All right, one more. Find the probability that a pet is a cat given that it's a male. Given that is your condition, it has to be a male. Male is a sure thing. You're picking from the males, so your bottom number has to be your males. There are 14 males. Of those 14 males, how many are cats? So what's the subset cat? 6. So 6 out of 14 is 3 out of 7. So a 3 out of 7 chance of getting a cat if you have a male. Now, these two sound really, really similar. Very different probabilities. The trick to getting these correct is to make sure you nail down what your bottom number is first. Do the denominator first, because the numerator is always a subset of the denominator. So denominator first is best practice. You're less likely to make a mistake if you nail down what's on the bottom first. Okay, so if you have counts, as we have here, you don't need any special rules other than the given goes on the bottom. So summarize that. If you have counts in a contingency table, or even in a paragraph for that matter, calculate the probabilities as we did on the previous slide. No special rules are required. However, if you have percentages, the percentages don't add up to 100% in both directions. They will only ever add up to 100% in one direction. So contingency tables are not very handy for percentages. We generally don't use them for percentages because they only read correctly in one direction. So if you have percentages, you're going to get percentages probably from a paragraph, and you will need a formula. So here's the fancy schmancy formula from the blue book. probability of B given A, of B happening if A is a sure thing, if A is already done, it has happened, is probability of B and A both happening, so the intersection, over the probability of A. Okay, so the top is the probability probability of both. If I could spell, it'd be dangerous. Probability of both and probability of just A. Even with this formula, it's a good thing to pin down the denominator first, because the numerator is still going to be a subset of the denominator. If you think about a Venn diagram, if you have two events, A and B, probability of A is going to be everything in this circle, and then the probability of B and A is the intersection of A and B, so it's everything in this part. So we would take everything in the whole circle and put it on the bottom, which is usually a percentage, usually a decimal form, and then the part where the overlap is a subset of circle A, and that's what's going to go on the top. So you don't actually need to do necessarily a computation for the top. Normally you already know the percentage that's in both, or the percentage of both happening. You already know what's in the intersection pretty much always. Okay, let's see the formula in action. Now we have percentages, things get a little touchier. In your textbook, 48% of the pages have data displays, 27% of the pages have an equation, and 7% have both. Now, keep in mind, the 7% that have both are included in the 48 with a data display. So if we looked at a Venn diagram, which we don't have to draw, but I think it's important to kind of keep in our heads what that picture looks like. Okay, if we have data displays and we have equations, we'll call those D and E, and 7% of the pages is both, that's the intersection. 48% of the pages have a data display, which means the entire data display circle has 48%, which means there's 41% in this moon-shaped section, 48 total in the whole circle. And in the equation circle, there's a total of 27, which means 20% have to be in this moon-shaped section off by itself, because the 7 and the 20 have to add up to the 27%. Okay, you don't need the picture to do the problem, but it'll help reinforce where those numbers are coming from. What is the probability that a randomly selected page, so we're going to pick a page, has a data display given that, okay, there's surefire proof that it's a conditional probability, given that it has an equation. So probability of a data display given that it has an equation. Okay? I can't do counts because I don't know the counts. I have to do percentages, which means I need a formula. So the formula says take the probability of the intersection of data and equations, or in other words, what percentage have both things on them, over the probability of equation. The denominator is always the event that comes in the given, after the slash. All right, and you always have an intersection at the top, so the order doesn't really matter for those. Okay, so what's in the intersection? Well, you have 7% of pages with both. What is the probability of getting an equation? Well, that's the entire equation circle. The whole circle is the 27%. So out of 0.27, 27% of pages with equations on them, 7% of those also have a data display. So the top is a subset of the bottom. And from here we need our calculator's help. So we'll grab our handy dandy calculators and we'll divide 7 by 27. And that will give us approximately 0.259, or about 25.9% chance of that happening. All right, let's look at the second one. What is the probability that a randomly selected page, one page, with a data display also has an equation? So it's a page with a data display. It has a data display. For sure, there's a data display on it. That's given. This is a given. That's your condition. So data display is your condition this time. So we want to know the probability that we also have an equation given that it has a data display. So here's a case where it's worded a little bit differently. We don't have those magic words given that. If you could rewrite that sentence and throw in the words given that, that's doable. What is the sure thing? That's your condition. Okay, we have a formula. Probability of having an equation and a data display, the intersection, over the probability of just a data display. All right, we do the bottom first. Data display is 48%. All of that circle is 48%, or you can use the 48% from your problem stem. Whoops, wrong place. And the numerator is the intersection of equation and data display. So how many have both? And that's the 7%, so 0.07 over 0.48, or 7 divided by 48 if you're going to pick up your calculator. That might be quicker. And then when you divide that, it's going to be about 0.146. So less chance of that happening because of the bigger denominator. Okay, so the good news is you don't have to memorize the formula, but you do have to know the notation so you can find the formula when you need it in your blue book. Okay, now let's go back to that addition rule we just learned yesterday and kind of combine it with the conditional probability that we just did. All right, we got a deck of cards. We're going to draw one card from the deck. What is the probability that it is an ace or a red? Probability of ace or red. Okay, we've got two options. One, draw a picture. And the picture will count as work if you do the picture. So if you prefer the picture, kind of go off to the side, draw yourself a Venn diagram, and put aces, put in reds. We know there's some red aces, so there's some overlap. Out of 52 cards, 2 of those cards are red aces. There are a total of 4 aces, so there are 2 aces that are not red. There are 24 cards that are red that aren't aces. Total of 26 red cards. And that's all we're going to need for this one. So probability of an ace or a red. So you could add these 3 together and get 2 plus 2 is 4 plus 24 is 28 out of the 52 cards. And 28 out of 52 is 7 out of 13. Or you can write that as a decimal if you prefer. So you could do it with the Venn diagram, okay? So with a picture, with a pick. If you use the formula, and some of you will prefer the formula, some of you will prefer the picture, I don't care which one you use, okay? If you use the formula says you got to find the probability of an ace plus the probability of a red, and subtract the probability of an ace and red, or the intersection of ace and red. Okay, because ace and red overlap, and these 2 are included in both circles, we would count them twice. These 2 get counted in both probability of A and in the probability of red, and we have to take out the extra. So probability of A, well, aces there are 4 out of 52. Plus red is 26 out of 52, or you could say 1/2 if you'd rather. But I'm going to leave a common denominator because then I can subtract them more easily. Okay, so I've counted in the 4 plus 26, I've counted that 2 in the middle twice. I need to take out the extra one. So take out the 2 that's in the shared part. An ace, that is red. There are 2 of those. Ace and red means cards that are both, have both attributes. So 2 out of the 52 cards are red aces. This doesn't mean to multiply. This means the intersection. What's in the intersection? That's what we want, just one number. All right, when you add and subtract, 4 plus 26 is 30. 30 minus 2 is 28 out of 52, which is 7/13. So you can use the formula, or you could use a picture. Either is quite sufficient for work on the AP exam. On the AP exam, bare minimum, you would need to show this computation right here, or draw the picture and then write down your probability. The picture counts as work. So you have options. Use the one that works best for you. There's no conditional probability here. This is just a straightforward OR case where we add. All right, 2 more and we're done. I draw one card and look at it. I tell you that it's red. Guess what? Red is a sure thing. That is a given. It is red is given. It is a given condition. It is true. I know it. There's no doubt. Okay. What is the probability that it is a heart? Okay. So probability of a heart given that it's a red card. Now, can you count cards? Can you do counts? Sure you can. So you don't need a formula for this one. So without the formula, you just count cards. You put red cards on the bottom. How many red cards do we have in a deck? 26. How many of those red cards are hearts? Half of them. So 13. And 13 out of 26 is 1/2. So you could use counts, or you could use a formula. If you want to use the formula, you do probability of hearts and red hearts, intersection, over the probability of red, which is the formula for conditional probability. Then you have to do some probabilities. So probability of a red card is 1/2, or you could say 26 out of 52. So we'll say 1 out of 2 cards is red. Red hearts, well, let's see, how many hearts are red? 13. How many of the red cards are hearts? What's the probability of a red card having a heart on it? Oh, half of the red cards are hearts, right? So 1/2. What did I do that was goofy? I just really made a mess. I made a mess. Scratch that. Red cards. Out of 52 cards, 26 are red. So the probability of a red is 26 out of 52. Okay. Probability of a red heart. Out of 52 cards, how many are red hearts? Well, all of the hearts are red, and there's 13 of those. So 13 out of 52. Now I'm back in business. I did something really goofy back here, so just pretend I didn't. You have to get good at that. Now, the 52s actually cancel and leave 13 over 26, which is 1/2. You get the same answer either way, but the counts is easier because you don't have to put it over 52. You don't have to treat it as a probability, so counts are quicker, but the formula will get you there as well. So counts versus a formula, you pick. Whatever works for you is what you should do. One more and we're done. I draw one card and look at it. I tell you that it's a heart. Oh, it's a heart. For sure. Absolutely certain that it's a heart. That's the given. What's the probability that it's red? Now, some of you are sitting back there saying, duh, if it's hard, it has to be red, so the probability is 100% or 1. Okay, if you've already figured that out, that's fabulous. You're ahead of the game. I'm still going to look at the notation. Probability of getting a red card if it is a heart. Well, I can count cards for the best of them. How many hearts do we have? 13. How many of those hearts are red? All of them. So 13 out of 13, which is 1. Okay, so this is with counts. You could also use the formula. With the formula, you're just going to look at 13 out of 52 over 13 out of 52. 52s will cancel. So I'm not going to bother to write that one down. We'll just do it the one way this time. Okay, you need some practice. So on the next slide, you have homework problems to work on, and we will dig into the next little section tomorrow.